Assalamualaikum warahmatullahi wabarakatuh and good morning to Dr. Faizari, my supervisor, and also to the internal and external examiner, Dr. William and Dr. Vera. As of today, I would like to present on my FYP project regarding on the magnesium alloy AZ91D Nitrided gas tap analysis. So here will be the flow of my presentation where I will go to the introduction of my project, problem statement, objective, methodology, experiment variable, result and discussion, project limitation, and also ended with conclusion. As of the project, it will be focusing on the nitriding process. Nitriding process basically is a surface treatment to improve the wear characteristic of a metal, such as surface hardness, corrosion resistance, fatigue strength, and also affecting the microstructure profile of the metals. All this improvement is due to the nitride layer formation on the metallic surface. This nitride formation consists of compound zone and diffusion zone as shown in the picture. So this layer is formed due to the nitrogen penetration into the metal itself, which introduced into the nitridability concept. Nitridability is referred to the ability of the metal to absorb the nitrogen during nitriding process. During nitriding process, there are two significant parameters that greatly affect the layer, which are nitriding time and nitriding temperature. There are three nitriding methods which are commonly used nowadays. Those three methods are gas nitriding, salt-based nitriding, and also ion plasma nitriding, which also known as ion bombardment nitriding. All these methods falls under the category of thermochemical process of hardening the metal surface. However, the most suitable method for nitriding a magnesium alloy is gas nitriding. Salt-based nitriding and ion plasma nitriding is not suitable because of the nitriding temperature. It requires a higher nitriding temperature exceeding the melting point of a magnesium alloy. So therefore, the magnesium alloy will burn first before the nitriding process ever occurs. So gas nitriding basically is exposing the heated metal to the atmospheric nitrogen. Magnesium alloy has been introduced into a variety of applications and fields such as automotive industries, electronics, and telecommunication. Magnesium alloy also known for its excellent strength to weight ratio, where it has a low weight or lightweight metal but at a higher strength. It also possesses both good and poor mechanical properties, such as in terms of good property, it has high dimensional stability, good machinability, good fatigue strength, excellent biocompatibility, and also has a low density. However, in terms of poor properties, it has low surface hardness, low melting point, and low corrosion resistance. Therefore, proposing a nitriding process is used to help to improve the mechanical property limitation of the magnesium alloy. The problem statement of the project is that magnesium alloy is a popular metal which has been introduced into industries. However, there was a little study was made on the nitriding a magnesium alloy, where most nitriding studies were made on carbon steel or titanium. Therefore, the best parameter setting for nitriding a magnesium alloy is remain unknown. Therefore, the objective of the project is to establish the correlation on the nitrided deformation on the magnesium alloy with the respect of the nitriding time. So here are the methodology of the project, where it consists of dimensioning sample, nitriding process, sample preparation, scanning electron microscope, SEM imaging, X-ray diffractometer, powder deflection, and also hardness test. Here are the 5 parameters used during the nitriding process. Every sample will have the same rising time, tube furnace rising time of 45 minutes at the constant temperature of 400. The difference for every sample is the nitriding dwell time or the nitriding time from 2 hours, 3 hours, 4 hours, 5 hours, and 6 hours. As for the result of the project, will consist of microstructure, SEM imaging, XRD, and hardness test. Here are the image of the microstructure for every sample. As for the untreated sample, there is no layer formation between the phenolic powder and the magnesium itself. However, for the 2 hours and 3 hour nitriding, there is visible layer between the phenolic powder and the magnesium, which occur in this area for 2 hours and this area for 3 hours. It also shows the same case for the 4 hours, 5 hours, and 6 hours of nitriding time, where we can see a boundary, a layer between the phenolic powder and the material itself. So in the 4 hours, we can see around here, 5 hours is around here, and 6 hours is around here. However, it's highly to note that for the layers that we show clearer in the SEM imaging process. As for the microstructure, is basically to assess the quality of our sample preparation before we going to the next step, which is SEM imaging. Here are the tabulated data of the SEM imaging and the depth layer formation. For the 2 hours nitriding time, the average depth was measured at 2.6 micrometer, and it keeps increasing steadily up until 6 hours. As you can see, for the 3 hours, the average depth was 3.6 micrometer, where 4 hours, the average will be 4.4 micrometer, 5 hours will be at the average of 4.93 micrometer, and for the 6 hours, which will be the highest average depth at 5.4 micrometer. Here are the line graph representing the tabulated data given just now. The line graph here, the orange line graph here representing the average value of the nitrate depth layer. As you can see here, from 2 hours to 4 hours of nitriding time, the depth layer formation occurs at the same rate. However, after 4 hours of nitriding, the nitrogen becomes a little bit slower, and after 5 hours, it becomes more slower than the previous one. This nitriding depth layer formation rate can be represented in terms of gradient value. As you can see here, 2 to 3 hours and 3 to 4 hours have the gradient value 0.95 and 0.88, which are almost the similar value, is the close value. However, for the 4 hour to 5 hour of nitriding time, the gradient is 0.5, which is almost half of the previous one, which show that the reaction rate or the nitrate depth layer formation be half slower compared to the previous one. And from 5 to 6 hours, the gradient value is 0.17, which almost one third from the previous value, 0.545. This show that after 5 hours of nitriding time, the depth formation layer become the most slowest compared to all the parameters set in this project. So the image here are the image which have been captured under SEM at the 3000 magnification scale. For 2 hours, we can see clearly the formation here, which are around 2 point something. And for the 3 hours, we can also clearly the nitridate layer formation, we also have the depth around 3 point something, 3.5, 3.7. As for 4 hours nitriding time, here are the nitridate case layer, nitridate depth layer, which is recorded around 4.4, 4.7, and 4.3 micrometer. And here are the 5 hour nitriding time, where the nitridate layer record around 5.1, 4.6, and 5.1, which are we have lesser significant difference compared to from 4 hours to 3 hours of nitriding time. And here show the 6 hour nitriding time, where the value recorded are 5.1, 4.8, and 5.4, which also show a less significant difference between 5 hour nitriding. And the right one here is the control sample, where we can see there is no layer formed between the phenolic powder and also the material here, the magnesium. So now we'll be focusing on XRD result. Unfortunately, no data can be gained since the slot for XRD have been fully booked. This is because of the time constraint we face due to the COVID-19. FYP students are allowed to return to UTP to do their experiment after week 6, which are in the middle of the semester. So which left for me around another 6 to 8 weeks for experiment. Not only that, to make it worse, the nitriding process took 1 day for one perimeter. I have 5 perimeters, which means that I have 1 week allocated just for nitriding only before progressing with another step. So therefore, with the limited time, with the long time consumption, I am unable to gain the XRD result. Now we will proceed with the hardness test. Unfortunately, no result can be gained. This is because of the equipment failure. For your information, UTP has a Vickers testing machine and Rockwell testing machine. However, for the Vickers, currently is offline because of the damage done by the previous student. However, for the Rockwell is in a great shape, but the issue I facing is that he have the improper indenter. The suitable indenter for magnesium alloy is scale A, B, and E. However, for the scale B, due to my thickness, the sample thickness of 0.4 centimeter, 0.4 centimeter, the scale B produce a negative value in the hardness test, which is invalid. Therefore, no result can be gained for the hardness test. So the discussion for the result is that the trend for nitrided depth layer is become plateau after 4 to 5 hours of nitriding time. This indicates that there is a lesser reaction between the magnesium and nitriding after 4 to 5 hours of nitriding time compared to the nitriding time of before 4 hours. So it is expected the maximum average nitrided layer is around 4 to 6 micrometer. This shows that the nitridability of magnesium is around 4 to 6 micrometer for every layer. So before 4 hours of nitriding time, the reaction between the magnesium and the nitrogen is become vigorous. So the gradient can also represent the reaction rate between the magnesium and nitrogen. So based on the trend, we can easily say that the longer the nitriding time, the deeper the nitrided depth formation. However, after 4 hours of nitriding time, after 4 to 5 hours of nitriding time, the reaction of between the magnesium and nitrogen become lesser and lesser. So the plateau is expected to be around 7 to 10 hours of nitriding time. After that, there is no reaction took place between the magnesium and nitrogen. So as you can see here, the nitrided depth layer formation trend from this graph can show us the best and the optimum nitriding time for the fabrication in terms of in the industrial perspective. For this setting, the optimal nitriding time is around 2 to 4 hours only. However, if the design requires the nitrided to be more than 5 micrometer up to 7 micrometer, it is advisable to prolong the nitriding time. However, if the design requires to have the nitrided layer depth around 10 micrometer, with the current knowledge and finding, it's hardly to see that the magnesium can achieve that layer. Basically, it's impossible. With the current knowledge, I can say it's impossible to reach 10 micron layer because of the trending. Because after 4 hours, the trend will start to plateau, and the plateau becomes significant after 5 hours, where the value of the gradient is around 0.17, and it's expected to be that after 6 hours, the value of gradient is around 0.0 something. So it's very, very low and very, very inefficient in terms of industrial perspective. So, determining the efficient time can help improving the process time, make it shorter, less nitrogen consumption, same nitrogen time become shorter, reduce the fatigue rate of the nitrogen machine, well, where less usage is occur, reduce waste in terms of nitrogen gas, cost saving where the nitrogen gas will be used efficiently, and also will increase the productivity of the nitrided magnesium product. Theoretically, the nitrided from the result, the maximum nitridity or the maximum nitridability of the magnesium is around 5 to 7 micrometer only. It's highlighted that the recorded result is based on the several assumptions. First of all is nitrogen gas speed, and secondly is nitriding pressure. The nitrogen gas speed cannot be quantified in this project during the nitriding process because of the limitation of the nitriding equipment. Another thing is nitriding pressure, which also cannot be quantified and cannot be controlled due to the limitation from the equipment itself. It doesn't have the proper equipment to measure and control both of these parameters. There are a lot of limitations when I'm doing this project. First of all, is time constraint. This is because due to COVID-19 and the new norm inside UTP. Another thing is to consider is the equipment availability, such as including inefficient equipment such as the nitriding process, where it requires 1 day for 1 parameter of nitriding. Even the nitriding parameter is only involved for 2 hours only. Another problem is that equipment breakdown due to mismanagement from the previous student. So the conclusion from this project is that nitriding deformation of magnesium alloy became plateau after 4 hours of nitriding time. Nitriding layer becomes deeper as the nitriding time increases until a certain nitriding time of 8 to 10 hours of nitriding. Theoretical maximum depth achievable for magnesium alloy is around 5 to 7 micron using the same setting and the parameter given in this project. The recorded data take place in a specific location and hardly can be present for the overall sample. And that's all for me. Thank you, and I'm open for the Q&A session.